we have an Atwood situation. This is problem 8. We have the Atwood situation, weight 1, weight 2, 4 Newton weight, 5 Newton weight. The 5 Newton weight descends 0.6 meters, and we're asked to do vector diagrams that depict the changes in potential energy of this weight and this weight. And the total of those changes in potential energy will be the change in potential energy of the entire system. Now obviously, if this weight descends 0.6 meters, this weight is going to ascend 6 meters, unless we have some kind of an elastic cord here, and that could be really interesting, but you don't want to go there today. Okay, so if the 5 Newton weight descends 0.6 meters, then what we've got is we've got 5 newtons, and we've got 0.6 meters. And the dot product of these two forces is going to equal the change in potential energy. And for the other, we have 4 newtons acting downward, and we have a 0.6 meter displacement upward. So the delta PE 1, which we'll implicitly use to label the change of potential energy here, equals negative of the 5 newtons times the 0.6 meters. Negative because the potential energy change is the negative work done by gravity. Over here, and get out of the way so you can see what I wrote there, but you got delta PE2 equals the negative of the work done by gravity on the system, but that's the negative of we'll say negative 4 newtons times 0.6 meters, and that equals, well, we haven't said what these equal. You could, and let me modify this slightly. It's not necessary because we know that this work is positive, therefore the potential energy change is negative. But let's just say that if we're in the y direction, both of these, both the force and the displacement will be negative. And then the negative of the product of two negatives is negative, and we get negative 3 joules. And over here we get positive 2.4 joules. 2.4 newtons times meters is 2.4 joules. Now let me put a plug in for always writing the units on all your quantities. It avoids all kinds of errors, and it's good form. You don't know what the quantities mean if you don't see the units. You have to look back at the problem to see where that 5 came from, or where that 4 came from, or where that 0.6 came from. Whereas if you put the units on it, it's always right there, and you're able to think about what you're doing rather than just grinding numbers to get a right answer. It builds better insight. Okay, in any case, the delta PE total equals delta PE1 plus delta PE2 equals negative 3 joules plus 2.4 joules. Okay, and I'm blocking that, I know, but this should be fairly clear. Equals negative 0.6 joules. Now you're also asked to find the speed of the system at that point. The delta KE plus delta PE equals 0 in this case. Why is this? It's because we're assuming there's no frictional force, so that that's the work done by the non-conservative force. So the delta KE equals the negative of the delta PE, which is going to be plus 0.6 joules. And if the system starts from rest, then you can use this to set equal to 1/2 mv squared. Its final kinetic energy will be 0.6 joules because it starts from rest. It started with zero and changes by 0.6 joules. Kinetic energy will be 0.6 joules. Set that equal to 1/2 mv squared, and you have the result. And you have the result without resorting to the equations of motion. Now, many students did resort to the equations of motion here, and you don't want to do that in an energy analysis. You're getting your hands dirty with details that you don't need to worry about. So, and you're also using a technique that can give you additional information. You have to use it in some cases, but also obscures certain information and certain concepts. So you want to get used to doing the energy analysis here. Now there's more to it, and we'll go just a little further, but I'm going to need another board. Summarizing the result we got previously, here's our system. The displacement of the system is 0.6 meters, and that implies by what we just saw that the potential energy change is negative 0.6 joules. If there's no friction, then because the work done by the non-conservative force is zero, presumably there are no other forces, including no friction. And since that is equal to the change in potential plus change in kinetic energy, it's equal to zero. Change in kinetic energy is negative, the change in potential energy. You want to focus everything into this equation in order to be sure you're doing your energy analysis correctly. Now, in this situation, friction is 0.06 times the total weight. Total weight of the system, assuming that the cord and the pulley are light, don't contribute significantly to the weight, is going to be 5 newtons, 4 newtons, going to be 9 newtons. Total weight pulling down, and the friction's up here in the pulley. The harder you pull down, the more friction you get in those bearings. And if we have this 0.06 times the total weight for the frictional force, we end up with a frictional force of 0.54 newtons. Now, how does that change our result? Well, that gives us non-conservative force acting on the system, and that's going to be the negative of the magnitude of the friction times the direction of motion, because the friction opposes motion. So that's going to be negative of the 0.54 newtons times 0.6 meters, and that's going to equal 0.06 times 0.54 is what, 324? Okay, so I think that's 0.324 joules. Now, we got a significant figure question here. I'm going to say that's approximately 0.3 joules. Since we've only calculated everything else to a single significant figure, we'll calculate this to a single significant figure. So that implies that delta PE is not delta PE, delta PE plus delta KE equals, I forgot the negative over here. Of course, it's negative of this times this. The frictional force being in the opposite direction, so the displacement makes it negative. And so that becomes negative 0.3 joules. Now, what does that do to our kinetic energy? We know the delta PE, that doesn't change. The gravitational force is still there. That whole analysis is fixed. It doesn't depend on how much friction there is or how much of anything else. If this system moves 0.6 meters, then you have the negative 0.6 joule change in potential energy. Okay? Now, if you put that together with this, we find that we're going to bring things together right here. we get negative 0.6 joules plus change in kinetic energy equals negative 0.3 joules, which implies that the change in kinetic energy is 0.3 joules rather than the 0.6 joules that we would have gotten here. Again, we didn't have to resort to analysis of the motion. We just analyzed the energy and we got this result more easily than we would have gotten it if we'd have gotten our hands dirty with analysis of the motion.